Now, our session today is going to be dedicated to torsion. You have seen torsion already in your previous courses. Now, in this case, we are going to discuss the Saint Venant method or formulation for those cases where the section of the shaft or the member that you are subjecting to torsion is non-circular. So that's the kind of the purpose of using Saint Venant's method. It doesn't mean that you cannot use Saint Venant in circular sections, as I'm going to show you by the end of the session. But it means that if you have any other section than circular, then you would be able to apply, let's say, calculate the stresses caused by torsion in those members. There is a particular characteristics of torsion, and that is that when you have a non-symmetrical or asymmetrical, let's say, section subjected to torsion, then, for example, the torsion is given, or let's say the whole piece or element is going to try to rotate or twist, that's the word, about one axis that is called the shear center of or the shear axis of the element, which might not be coincident with the centroidal axis of the piece. So that's a very important, say, characteristics of this. So, and what I have here already drawn is a small element. It's a kind of just an element. This is an element that is fixed on one side, and there is a torsion applied to that element. Then obviously, if you kind of remember how torsion works in this sense, you're going to notice that we're going to have, for example, if I draw a reference line from this point to this point, and then by the application of the torque in this sense, this reference line is going to kind of change from this point to this point. Maybe, not straight line, but it's going to twist. So this is the classical torsion figure you have seen. Kind of this is going to rotate. So before jumping into Saint Venant's method or formula, I'm going to discuss what we have learned in the past and everything we have noticed or done in terms of rotation of elements by applied torsion has to deal with the Coulomb's theory. So let me write it down here. And one thing that is said there is that, let me draw a kind of a view of this element from this side here. To take this out, this one here. And if I draw that circular section, in this case, I'm going to assume that it's a circular section for the Coulomb theory point of view or demonstration. We remember that in this circular section, and then I'm going to draw a reference axis here. Let me move it to the center, more or less here. Let me draw it again to do it maybe better. Yeah, from this point to this point. Being this X, for example, and this Y, we've seen that the distribution of stresses caused by that torque is something like this. So you're going to have some sort of triangular form here. So you're going to have a reference line here, and that's going to be the shear stress is going to increase until a certain point, and that point is going to give me kind of the maximum shear stress at the end of the element here. Let me draw a couple of more arrows here. This one, for example, and another one. Something like that. Yeah. So this is the shear stress due to the torque applied to these elements, so meaning that the torque goes in this direction here. And if I wanted to bring some of the classical equations used to calculate torsion or stresses due to torsion in this, let's say, very circular and kind of axis symmetrical section, it would be something like this. So we remember that that was like, for example, the torsion equation was for this element was something like the torsion equation. Something like this, the torque, divided by the polar moment of inertia is kind of something like this. This is G, which is the shear modulus of the material is the equivalent of the Young modulus kind of in normal stresses, but in shear stresses is called the shear modulus. And this multiplies by the by theta here, and this theta is just the twist angle, and this twist angle is dependent on the kind of direction. So angle of twist, or let's call it twist angle, and it depends on this direction z. Or no, it's not that depends on direction c. The correct way to say is that this is the twist angle is measured in degrees per longitude units, meaning that it depends per longitude units, meaning that it depends on where you are measuring. Then this twist angle represented here is the one that is going to tell you this. Let's say whatever you measure, you're going to have a respective twist angle there. Now this is what we have done. But what about if my section is not circular? Kind of, what if I want to have a different type of section or something presented there? So and there is where same Venant comes into play. In this course, we are not going to go that far to calculate complex non-symmetrical sections, but I'm going to leave you with the concept of it because you're going to get a more in-depth knowledge later about it. So let me continue then and draw this non-symmetrical section. So it would be something like this. So I'm going to have some sort of, maybe here, yeah. So I'm going to have a non-symmetrical section. I'm going to draw, again, Cartesian coordinate system. And I'm going to draw it like this on purpose to let you know that it doesn't have to be in the center of that shape. Actually, shear centers of certain geometrical figures are outside of the physical bounds of the figure. So they are not found in any of those parts there or placed kind of inside of the physical, let's say, or bounded material of that. Might be outside of that. Then if I assume that this section here is a section that I took by cutting this element in this I kind of position located at z units from the fixed part, then this is going to give me something like this, and this is going to be the point 0. This is going to be the x-axis and y. And to understand what starts happening with before and after I apply torque to that element, I'm going to have something like this. So I'm going to draw a point here. So this point P that is going to have coordinates x and y is going to be located at a certain distance from the origin of this piece. So let me draw it from here to here. Then this point is going to have a certain angle with respect to the x direction at alpha. And if I wanted to bring right now some sort of geometric relationship between, what's happening with that point, then I could kind of try to extract this Cartesian coordinate system and the point. And I'm going to have something like this. So it's going to be, do it again, Cartesian coordinate system. I cannot, well, I will draw it here and I will move it to this place. Yeah. Then I'm going to have the point arbitrarily selected, P, coordinates x, y. Then I'm going to have the line connecting the point, and this is going to be the angle alpha. Now, the kind of, if I wanted to know the segments or how to go from the origin of this Cartesian coordinate system to the point P, so I would have to travel certain distances in x and travel a distance in y. So I want to write that. The trigonometrical relationship for those would be something like this, that the sine of alpha equals y, this point here, divided by some radius, and I'm going to, or some distance r, not a radius, a distance r, let's call it that way at this moment, but it's going to be a radius later. So this distance here, and the cosine of that angle is going to be then is x divided by that radius. Now, this is pretty simple so far. One of the things that's happening or that is interesting here starts when I applied a torque here. when I apply a torque, what's going to happen is that this point here, point P, is going to move, it's going to twist, kind of that section is going to twist. And two things are going to happen when applying torque to a non-symmetrical section. Let me first write that point. So let's imagine that the kind of the movement of this point after applying torque is going to be located here. Now, let's consider that the distance or the kind of the movement of this point to this part, point P prime, is very infinitesimal. I mean, it's very small. Uh, so this theory, most of these theories, even the beam deflection theory, are based on kind of on the assumption that deformations are pretty small. And even though I'm writing it or drawing it pretty large here, this is considered to be pretty small, pretty infinitesimal. Then when I apply this, of course, this is going to, let's say, be rotated, kind of following some sort of arc. But as it is very small, then this arc can be considered a straight line here. And it's going to be a straight line that the path is going to be 90 degrees with respect to this one. But in any case, but the important thing is that according to St. Venant, the whole formulation, when you apply torque on a non-symmetrical section, two things happen. First, you're going to have the twist of the section. So each section that you're going to have in here is going to twist. Let me see if I can just draw a couple of sections. And that twist is going to correspond to those, let's say, to that twist angle there. So each section is going to twist. Let's put it at CC. And for example, the angle in here, the twist angle in the I section is going to be smaller than, for example, in the CC section, and so forth, as long as when you're moving to the end of this piece. Now, because of this non-symmetrical condition, then torsion is not only going to create a twist, which is going to induce shear moment, shear stresses, but it is also going to induce warping or cause warping. So the whole, let's say, the phenomena happening here are twist plus warping. And warping, if I wanted to write a definition of it, I'm going to write it here so we can have it all at hand. Warping is kind of, as a definition, is the deformation, but not in angular way, but extension deformation. I'm going to write extension deformation in the direction of the axis about which the torque is applied. Let me write it down then, if I remember. In the direction of the axis about which that torque that I'm showing there is applied, or in general. Great. So you're going to have a couple of things happening there. And that's why column theory applied directly to non-symmetrical sections gives certain erroneous results on that. And to overcome those results, then thanks, St. Venant came in and then proposed something that we're going to see right now. Again, for me, I have mentioned this before, that is amazing how theories already from 200 or 300 years old are still perfectly valid, and we keep using them, and we keep, let's say, using it as using them as foundations for many of the designs we have done as a civilization. That's it. So, but how warping looks like, I kind of brought a couple of pictures from the internet. I'm going to move them here. This is the first one, and this is the second one. And this is a representation of what warping would be in I-beams, for example. You have one end fixed, and then you apply torque to the end. This is called restrained warping, and it's also considered like non-uniform torsion, and it has different characteristics, but the figures are pretty well showing what warping means. What we're going to deal with here in this course is about uniform torsion. So, and they have different characteristics. And then here, for example, if you apply torsion here to this I-beam, which is fixed at the end, something that you're going to warping, what it's going to do because of this extension is that you're going to induce bending moments in this area here. In this, for example, in the flanges of the beam. So here you're going to, because of the torque, you're going to induce bending moments, which are going to kind of cause also normal stresses on the structure. And there's going to be a change, kind of a difference in length. For example, you see here that there's a marked difference here, even though it's just a representation without any scales. That means that this is going to happen. So meaning that many of the assumptions we have taken during the course when deriving certain formulations is that the plane sections remain plane to each other. You have heard that before, that for example, in a very uniform torsion that of a circular element, this section in CC, for example, is going to be parallel or yeah, to the section in II. Now, when you introduce warping, there is going to be deformation in here, meaning that this point I, after applying torsion, might come here, for example, and that's going to kind of, that's going to create that deformation or extension is going to create strains, and those strains are going to create stresses which corresponds to normal stresses. So that's something that might be happening there, and that's why Saint Venant takes care of that, and that's why we are taking a look at that in this course, even though it's in a very simplified way, because you have the notion when you go either to continue your studies or you are going to do any kind of work with these type of elements, non-symmetrical elements. You're going to say, well, the normal theory does not apply here. I need to apply a different one. Questions so far? Let's continue then. To continue with the development of this, I'm going to focus on this figure here. So the one where I apply the torque, and that torque will make this section twist, and point P that was here now is in P prime position. I'm going to extract kind of those 2 points here. So if I try to, I will draw it maybe again in here. So I'm going to bring a Cartesian coordinate system again, a little bit bigger. And I'm going to have, for example, point P in here. And I'm going to draw the lines again. Comes from this point to this point here. Yeah. And I'm going to draw the complete triangle from this point to this point here. And I said that this is going to be, let me mark it in black, alpha. I know that this is 90 degrees, and this angle here is going to be 90 minus alpha because of the kind of the sum of internal angles of a triangle is 180. Well, that's the consequence of that. This is point O, this is point P. Now, if I apply torque and that point moved, it means that that point is going to be somewhere there here. Again, this is a representation, P prime. And actually, let me put it bigger so difference looks better here. Then I'm going to have another color. For example, I'm going to have another triangle form, the vertical of this, and horizontal from here to here. Yeah. And then this one here. Great. I'm going to call this one point N. I know that this is 90 degrees. And because of what I mentioned at the beginning about considerations on how far goes from P to P prime, this is a very infinitesimal distance. This arc, basically, I'm going to consider it as a straight line, even though it's an arc. But as the kind of the deformation is pretty small, I'm going to consider it a straight line, meaning that this is going to be 90 degrees here. So this is going to be, again, alpha, this angle, and then that alpha is going to be repeated in here. A little bit messy, but just bear with me. Now let's analyze certain positions and distances. First, what's the position of point P? In this case, I'm going to mark it with this. That position is going to be right here. It's going to be at a distance x from the origin. And the kind of the height of that is going to be at a distance y. But then to move from P to P prime, I have to go in the negative direction on the x-axis up all the way until point N. And that's going to be, I'm going to call that x prime, or well, that's the kind of the distance from one to another is going to be x prime. And to go from N to P, well, I have to go all the way up to y prime. Okay. And another piece of geometrical consideration, let me write down the axis name here, is that the value or the length of this arc is going to be well known by by using that twist angle. So the twist angle is going to be, in a nutshell, or I know that that arc is going to be the arc that goes from P to P prime. And that's going to be equal to what? It's going to be equal to this distance here, which is represented by R, times this twist angle here. But this twist angle is going to be represented by the multiplication of the distance z times the theta, which is the twist angle. So if I wanted to write that, it's going to be R, which is the radius, times z theta. Great. This kind of the movement from P to P prime denotes, according to Saint Venant, a movement in 3 directions. Let me draw again that triangle here. So I have vertical line, horizontal one here, and this one here. So this is point P here, point P prime, this is point N. Then Saint Venant says that the movement that occurred from P to P prime happened in 3 directions corresponding to the 3 axes of the Cartesian coordinate system x, y, z. That is, first, it moved at a distance of minus u in the x direction. Then it moved at a distance v in the y direction. And in the z direction, it moved at a distance y, w. And this w is where presents the interesting fact about warping. So if I wanted to discover how much are each one of those displacements, I could write it in this way. First, the distance in x, u. I know that that corresponds from coming from negative, from coming from P to N, right? V, I know that comes from going from N to P prime. Now, if I know that this angle here is alpha, then I can bring the trigonometric formulas here and say, well, sine of alpha equals to that minus u. Well, let's put it in this way, u, but let's not confuse u, divided by the distance P prime. And the cosine of alpha goes to that V divided by P prime. Right. Now, knowing already that that distance of that line P prime, even though I'm saying this is an arc, but as it is very small, I'm considering it to be a straight line here, then I can find out certain interesting relationships here. So for example, if I substitute this one here on this one here, I'm going to say that U equals to minus R Z theta times the sine of alpha. And that V equals to R Z theta times the cosine of alpha. This is awesome. But this doesn't end here because I already know that the value of those trigonometric relationships, like shown in here, can be related to the coordinates x and y. Now, if I bring that to here, I should copy it just to have a reference. And put it here. By using these friends I have here, I can now write this equation into U, black, equals minus R, Z, theta, and sin of x, sin of alpha is going to be y divided by R. And V, going to have that R, Z, theta times cosine of alpha is going to be x divided by R. I'm going to mark these equations. Well, not yet. The other component I need to write down here is W, which is the displacement happening in the z direction, and that is happening because there is warping here, and we don't have a straight, let's say, definition for that. We only know that that's going to be a displacement in the z direction that is going to be represented by a special function. That function has a name that people have adopted during the whole development of the Sine-Venant process, or Sine-Venant starting it with. And that's going to depend on x, y, and the twist angle. So warping, in the sense, is going to be represented by a function of x, y, and theta. And we could write down that W, which is a displacement in the z direction, is going to be then a function of theta times another function, psi, which depends on x and y. And this is where warping gets introduced in the whole formulation. Because we're talking about a displacement in the longitudinal axis, which we haven't considered before, but it's going to happen, and that's going to create certain irregularities. The beautiful thing about Sine-Venant is that it is a theory that allows us to separate what is torsion to what is warping. So we can treat it not definitely, but we can treat it as independent individual quantities to see the effects of each one of those, but it's something that Sine-Venant is allowing us. If I continue a little bit with these two ones here, I'm going to have that U equals to, I can cancel the R's here and also here. Then I will have that this is equal to minus Z theta Y, and V is going to be Z theta and X. Then we end up having the displacement, let's say, values, or let's say way to describe the displacement of that point once you have applied torsion to the element. Why is this? It's pretty important. Something that we have also mentioned is that in the whole concept of what we have been doing here in strength of materials, or kind of solid mechanics, is that at some point you can take it from any starting point to any end, is that you have forces applied to an element. That force is going to create, or create and cause an stress on the part that you are applying those forces or loads. Then thanks to the constitutive law of meaning, the material, or how you describe material properties, I'm just going to raw material here, write material. Then those stresses are going to create or develop strains and those strains are going to end up being deformations on your element. So imagine the whole process that, most of these theories or even the development we have done in the course have been something like that. You start by defining forces, find stresses, put together a material, then, calculate strains that will end up in deformation. However, in this case, we're talking about displacements from one point to another that I could equate to being deformations. So, I mean, that's why I said that you can start with any end and end with any other part of the whole chain that I mentioned here. So I can say this, meaning that if I know these quote unquote deformations, which are the displacement of this point to another part from the, let's say, unloaded to the loaded configuration, then it might be possible that, and actually I should write this like this, that I can calculate strains from those deformations. And let's see what's happened. So strains, by definition, let's write it down here. But before that, is there any question? If you have a question, please interrupt me. So let's see what's happening here. So we have the deformations of that. And let's see how are the strains there then caused by those deformations. So let me write it down actually in here. Yeah. So strains, for example, in the x direction equals to the partial differential of this displacement with respect to x. Now, if I do this with the formulas I have or the relations I have just found, it would be equivalent to say that it would be the partial differentiation of this term here, that I'm now realizing that it does not depend on x, meaning that there is no any strain in the kind of in the x direction or longitudinal, the normal x direction. If I do the same in the kind of y normal direction, if we remember, for example, a similar concept to a state of stress represented by an elementary cube that we have drawn, for example, normal stresses and shear stresses and stuff. So more or less the same. In this very kind of particular case, I'm going to have this is going to be the partial differentiation of this v here with respect to y, and that's going to be the partial differentiation of partial derivative of this term here in the y direction. Now I also realize that none of these terms vary according to in the y direction, so this is always 0. And let's continue with the z direction. So epsilon z equals to the derivative of w derivative of z, and then that's going to be equal to, let me write it better, of the term that it kind of, let's say, represents the warping of my whole problem here. It's a little bit bigger. Now, let's see, I also see that none of these terms, uh, varied with the z direction. You say, well, but what about the twist angle? But you said that depending on the z direction, you're going to have a value of the twist angle. Yes, that's true. But that twist angle is not a function of the z direction of the z axis of the z, let's say, component. It's just kind of just a value of, for example, this many radians per millimeter, and that's it. So there is not really a dependency on this consideration of theta with respect to the z axis or the z component, meaning that then this follows the same fate of the previous two, and this equals to 0. Okay, we found 3 components out of the 6 needed to represent this elementary cube. Let's find the other ones. Let's go to the, how to call it, let's say, this is kind of intention, kind of some shear strains. So let's start it in here, for example, with this gamma is going to be then, the definition of this strain in xy. is going to be equal to the derivative of this one, kind of are the complements, y plus derivative of v by partial derivative of x. And then, okay, let's do that. If I substitute these ones here, so I know that this is going to be d z theta y over partial divided by the partial derivative of y plus partial derivative of v, that is this one here, is z theta x divided by the partial derivative of x. And well, yeah, there is variation here, so let's just take the partial derivative of these terms correspondingly in y and x, and the first one is going to be minus z theta, and the second one is going to be plus c theta. And wait a moment, this is also it's giving me 0. Oh, what's happening here? Let's continue. We have gamma, then for example, zx or xz, because there is also reciprocity in these shear components of the strain. And I'm going to have then, let's see, this is going to be u z partial derivative of z plus partial derivative of w by partial derivative of x. And let's see what's that. So u is this one minus z y partial derivative of z plus then partial derivative of this one with respect to x, and w is this one here, and this is going to be theta, and a function that is kind of varies with y and z, sorry, x and y. Great. Then if I continue operating with this, I can partial derivate this term here, the first one, and that's going to be minus theta y. And the second one is going to be theta multiplied by the partial derivative of this psi function with respect to x. And I will write it kind of just like that, the partial derivative of psi with respect to x. I don't know, actually, I don't know what's the psi function there. And then if I kind of simplify a little bit more, this is going to be equal to theta, then partial derivative of psi with respect to x minus 1. Then I'm going to do the same with the missing shear strain that I need to calculate there. I have xy, zx, and then I need to have yz or zy. Gamma yz, then that's going to be what? Partial derivative of p with respect to z plus partial derivative of w with respect to y. Then operating again, this is going to be the partial derivative of v, which is z theta x over the partial derivative of y, sorry, z, plus partial derivative of w, which is then theta psi, which is function of x and y. And then partial derivative of y here. Perfect. The same, keep operating. The first term, I can just partial derivative with respect to z, and that's going to give me straight away theta x plus theta that multiplies the partial derivative of psi with respect to y. And then again, I can write, or extract common terms here and say, well, this is equals to theta here, partial derivative of psi, or partial derivative of x, sorry, of y plus x. There's a mistake here. Yeah.
It was just about the previous one, about -1 and
Yeah.
-1. Yeah, no, it's fine.
Yeah, thank you. Thank you. I just saw it when I was writing below. Yeah, I had that mistake. Yeah, thank you. Great, so let me mark it here. So now what's the consequence of having this? What's the physical meaning of having strains equal to 0? Well, let me go back to this part here. So if strains are equal to 0 in here, or some of the strains are equal to 0, it means that there is nothing you can do on the material to cause any stress, hence, be equivalent to have a force applied there. So if a strain is zero, it is equivalent to say that stresses caused by that strain are equal to zero. So if I make a summary of this, and I can say then that, for example, epsilon x equals to epsilon y, epsilon z, and also this gamma xy are equal to zero. Then if we are also relying on Hooke's law, then I'm going to say that the stresses caused by those elements are non-existent. There. Right. But what happens with the other, I want to put a mark here. What happened with the other shear kind of strains that are happening? Let's see what type of stresses they develop or create. So let me see. Stresses, we know that stresses or shear stresses are related to strains, for example, in generic way as, the shear modulus times that strain. So if I apply this convention to what I have right now, then the shear stress caused by the corresponding shear strain, for example, in YZ, for example, that's the first one I'm seeing right now, is going to be equal to G, the shear modulus times this whole part of equation here, and that's going to be theta, open up this, let me write like this, x plus differential of psi, which is the function depending on, actually that's a function that depends on the shape of it's called boundary condition kind of dependent function, but that's something that is going to tell you how is the shape of the function of the section, and by knowing what's the shape, then it has a meaningful or relevant uh, part on defining if there is warping or not. So I'm going to have this one divided by y, yeah, and then if I do the same with the other one, mark it here, shear stress on Zx, that's going to be then G times the strain, shear strain there, and that's going to be theta times, we write it again like this, minus y plus the partial derivative of that psi function. Right. Now we're talking about strains. After strains, we're talking about stresses. Now it's the perfect moment to apply something that we have been applying different other parts of the course, which are equilibrium equations. Because I know that after I applied torsion here, they say, I just applied torsion and that's it. So this is not rotating on anything. So there's going to be an equilibrium in this element of the forces, of all the stresses. So just by leveraging that equilibrium, then we can say something about how stresses are behaving to each other. So let me then write the stress equilibrium equations. That was one of the first equations we wrote in the course, and they have this form. Let me write it like this. Stress equilibrium. Yeah. So as I know that that's not moving, I can say that. Actually, I'm going to write completely. So that's going to be you're going to recognize it as soon as you see. So partial derivative of normal stress in the x direction plus partial derivative of the shear stresses here in this direction plus partial derivative of this one in the z direction. And then I'm going to neglect that there are no body forces acting on the element. And that's why the other term appearing here, this b, if you remember, is not going to appear here. So I'm going to continue with this one. I'm going to have kind of this reciprocal here. I can write it actually in the same fashion because we already know that tau xy equals to tau yx because of the reciprocity of shear and stresses. Then I'm going to have this one here, 2y plus tau yz divided by z. And then the third line goes something like this. So this is the one, continues here. It's a very good mnemotechnic technique. This one goes with this one. Actually, no, this is the opposite. This one goes with this one. Z x plus partial derivative of, now comes this one, plus now this one. Right, better, equal to 0. Now let's analyze which terms are existing and which one are not existing. So I'm going to mark with red those that are 0. So I know that this is 0 because there is no normal stress. This is also 0, and this is also kind of in this sense. Mark it like this, x, z. Well, this is not 0. However, this equation doesn't do much here. Or actually, let's review this sigma yz. So the partial derivative of the stress xz, this one here, is 0 because if I try to do the partial derivative of this equation with respect to z, there is nothing here varying in z, then hence this is also 0. Does not depend on z. That's why it's 0. Then if I do the same here, xy shear stress is 0, this one is 0 also, and then the similar case, the shear stress in yz, this one here, does not depend on z. Let's see here. This one, partial derivative of the shear stress xz with respect to x. Yeah, because we have a function here that varies with x. And then partial derivative of this shear stress yz with respect to y. Yes, because there is a psi function depends on y, is varying. But then this one here, partial derivative of the z normal stress with respect to z. Well, this is also 0, actually. So meaning that the only two, let's say, possible equations here are these two. This one. I should just take these ones out and say, okay, so what's happening with these two terms? Basically saying that partial derivative of tau x z with respect to x plus partial derivative of the shear stress yz with respect to y equals 0. Let's see what's happening here. Then let's kind of operate, or let's construct this partial derivative. So let's take the first one, partial derivative of this shear stress. So I'm going to have that's the partial derivative with respect to s, because I know this is going to be a long term here, of this shear stress. And that shear stress is this one here, g theta minus y plus this one here. So this is turning to be a 2. I don't want that. Great. And what is this? So if I continue working with this is going to be doing that. It's going to be the partial derivative of the first term, this one here. So I can do it like this, minus g theta y plus, I can bring out g theta, partial derivative with respect to x of the partial derivative of this psi function, x. Yeah. And then I know that this is not varying with respect to x. So this is 0. But then the other part of this is that this is going to be equal to, or actually I can say that partial derivative of this shear stress here equals to g theta, then partial double square. Yeah. Let's do the same with the other one. The other is partial derivative of tau, tau, yz with respect to y. Then again, I'm going to write it again, y. And then I know that this one here is going to be this one here, g theta parenthesis x plus this other one, okay? G theta parenthesis x partial derivative of psi with respect to y. So to write down this. Then it's going to be equal to the first term as the previous one plus partial derivative, I can bring it out, g theta partial derivative of y of the first okay. Then I can write it down as final, semi-final form as this one here, which is j theta, then the second derivative of this side with respect to y square. If I compose these two equations into this one here, then I'm going to have the following form, which is a very particular form, and that's going to be, let's take the first one here, the tau xy resultant. It's going to be g theta, second derivative of this one square plus, let me see, yeah, g theta partial derivative of psi with respect to y square, and that's going to be equal to 0. I can work it better and say that, well, this is going to be equal to g theta, this function here, well, this second degree derivative here, plus this one here, y squared, that's going to be equal to 0. This form here is called the Laplace equation. When it's represented in this way, kind of you have a double differentiable equation in this form. And this is represented, and you're going to see it in many texts as kind of this inverted triangle, the Laplace operator, square, kind of psi equal to 0. Those g and theta, kind of the solution of this equation for this to be equal to 0, it has only one solution, and that's that the internals of these square brackets are equal to 0. And then because these are always assumed to have certain values, so these are not 0, then this is extracted in this way. So this is something called kind of the governing equation for torsion. Right? Then we are not done yet, because so we applied strain, so we had strains with stress equilibrium equations, but now it is important to know what happens in the boundary of the body, where there are supposed to be the largest shear stresses in appearing there in that section. So let's see. Let me draw again the a kind of just an asymmetrical body here. And I have a coordinate system. Again, doesn't matter, it doesn't have to be there, but xy. I'm going to have an infinitesimal element here, exaggerating the value in here. And I know that this kind of in this boundary, when we were analyzing stresses in the boundary of the body, kind of in the surface of the body, I know that there's going to be a normal kind of direction to that one here. And I know that there are certain stresses appearing kind of in these directions, for example. And we need to find out that because that's a point of interest. And then I also know that the line connecting the origin of the reference system to this one here is going to be kind of inclined at alpha. So just assuming that the point is located at the surface of the section of that element. If I extract that triangle a little bit larger here, I'm going to have one line here, the other one, just to form that triangle. I'm going to have as components of that triangle a distance here minus dx and minus dx, because remember that I'm moving from one point to another. In that sense, to be consistent with what we said at the beginning, we have a distance dy, and this is going to be this normal here, which is going to represent this normal stress. This is kind of the direction of it. Is going to be applied over an area ds, kind of the surface, and then again we're going to say that this is alpha. And let me write another reference system so to be clear with this. Yeah, yeah, this is going to be in x, this is going to be in y. Now, if we wanted to know the orientation of a vector as we have done before, we need to rely on what are the cosine directions of those terms. And let's remember that the cosine directions we've used in the past are L. Actually, let me give it a name. Cosine directions, L, M, and N. Now, because of the configuration we have there, cosine direction L can be said that equals to kind of this term here. Cosine direction M is going to be then the corresponding, yes, and cosine direction N, we're going to say that at that point is 0, even though let's say we are saying that the plane containing both points here, or both points P and P1, for example, are kind of there, or these 2 points, let's put it, these points are in the same plane, meaning that there are no any z component, that you need to find out using any direction cosines. That's not contrary to what we have said, that there is warping, and in warping the sections kind of are not parallel to each other. So it's okay, sections cannot be, in this case, parallel to each other. They can have any different, let's say, orientation, even kind of complex shape. However, if I kind of, for my calculations or the whole formulation, I'm saying that those 2 points I'm choosing to create this differential element, which is located in the surface, are in the same plane, then there is no any direction to take into account in that axis. Now, to understand what's, for example, if we have a vector S apply here, which is a stress vector in that direction, as a vector kind of here, this is a normal direction, then we could say that the components of this stress are going to be equal to, what we have done also when transforming from one system, one coordinate system to another in the first, let's say, topic we covered in the course. And that's going to be, for example, I can write it like, in the x direction, it's going to be what? Well, it's going to be the normal component times L plus the shear xy times m plus the shear xz times this other n. Now in y, I can say that this is going to be equal to xy L plus sigma y normal stresses in M plus, because if I could find, kind of what I'm doing here is that if I found the state of stress of this element by finding out, where was it? These conditions here, kind of I found out all of the 6 necessary elements to build a state of stress tensor, then I could find a way, another stress, with another orientation by finding out by using the same state of stress tensor and the direction cosines of this new direction. That's what I'm doing right now. And this then it goes to tau yz n. And then finally, in z direction, I'm going to have tau xzl plus tau yzn plus this normal stress z in n. I'm going to eliminate those that were 0, either because the stresses are 0 or because the direction cosine is 0. So I have this one, I have this one, and this one. All these 3 are 0. This one is 0, and this one also is 0. Meaning that what I end up having is something like this. That I'm going to substitute the values of these two stresses in here. In the equation, that's going to be that G. Actually, I don't remember them from memory. The first one is XZ. XZ is this one here. Can I try to copy it maybe? This one here. Yeah. Actually, I'm seeing this, and this may be missing at least one parenthesis here. So it's consistent. And then the other one, which is this one here. Plus, this multiplies L plus this one. That multiplies M. There's a mistake here, just putting it. This is not M, N, this is M. Yeah. And then this equals to 0. Now, I know the values of L and M, which are in here. So I have L is this, and M is this one here. Then I can substitute these two values in here. And that's going to give me that d theta, should I should put it larger like this, minus y plus the partial derivative of this psi function times dy ds plus this one here, x plus partial derivative of psi function with respect to y times m, and m is minus dx ds. And this equals to 0. Good. If I arrange a little bit this equation, I can write it in the way that I can group, for example, this term here, and I can, just bear with me. So I can get rid of this, as this is equal to 0, and I, for sure, these terms here are going to be different from 0. Then I can put it in the other side of the equation and get rid of them. But then I could rewrite this in this following form. So just to write it consistently with the terms, I'm going to write the first one like this. Psi divided by x minus y. Yeah. Then dy ds plus, actually, minus x plus dy write it, sorry, dy. I had to write this one before. Plus x, then dx ds equals to 0. Now, this equation here is known as the Saint-Venant formulation. So Venant. And this equation assumes, as mentioned, two things. That the deformation on a twisted shaft, let's put it in this way, deformation of a twisted, or this twisted shaft actually, because not any, twisted, yeah, shaft in this case, or element, consists of, the first one is that, was that rotations of cross sections, the twist, and the other part that kind of says, which is, the powerful feature of Saint Venant, is of the warping of, again, cross sections. Now, let's remember the warping is a deformation by extension in the direction of the axis about which the torque is applied, meaning in this case, this one here is along the z direction. So this is because of the non-symmetry of the section and the torque applied, there's going to be a deformation here in this direction. Right. Now let me make a pause for 30 seconds. I'm going to grab some water and we're going to continue. But 1 minute, just a pause. All right, let's continue with this. Now, what should we do? So yeah, this is not useful so far. So we need to find out an equation that allows us to calculate stresses on these type of elements. And for that list, then let's go to try to find out what would be a, let's say, corresponding torque equation according to a general case. So let me write it down here. Be in this place here. Using Saint Venant. Great. Then I'm going to draw again a, I should bring this one. I already have drawn it. Bring it back here. But instead of this, I'm going to draw just a representative element in the middle of this body. And just, it's going to be a square. Kind of in here. Just a square. According to what we have done so far, so this square is going to have a dx here, a dy here, and also, let's put it in this way. This is going to, the stresses applied to this element are going to be 2. The first one is going to be in this color. The only two stresses acting on this element are going to be shear stresses. And in this case, I'm going to have in this direction, for example, it's going to be stress tau yz. And in this other direction, the horizontal direction, is going to be tau xz. Now, if I wanted to know that the moment or the torque produced by these shear stresses on this differential area defined by dx times dy, I need to know definitely what's the distance from the application point that I'm going to take as being this center here, O, and then it means that to calculate that moment or torque caused by those stresses, it's going to be kind of the distances, perpendicular distances I'm going to have from the origin to each one of those, meaning application of that, those are going to be symbolically representing those stresses. Of course, something to be something like this. Then I'm going to have that a differential torque produced by those shear stresses are going to be what? For example, in the first case, it's going to be uh, this torque here, that is the, how to put it, the shear stress, YZ, acting on an area. So that's going to give me a force, so a differential area. And that's going to be multiplied by a distance x, where this tau z is going to be applied, meaning that I could take this one here and just to, as a representation, I could say, well, this is more or less something that's going to be like this. Yeah. Correspondingly, kind of if I assume that any torque trying to cause moments in this direction is positive, just taking that convention, then the other torque will cause some sort of negative moment, and that's going to be written in the following form. That's going to be this tau xz times dA times y. Then I can keep, let's say, operating this and say, well, this differential torque equals to, just going to take no common factors out of that, x tau yz minus y tau xz times the differential of area. If I wanted to know the torque caused, kind of by, look at this. So now we have moved to this direction. So we were here, so we found deformations. Deformation cause kind of found strains, use Hooke's law to determine stresses. Now we are kind of saying, okay, what would be the kind of the torque applied there? Basically, it's a load. So we have been jumping from this side to this other here. So if I wanted to know the torque that would cause those shear stresses and then that deformation at the end, it would be something like this. So I would have to integrate kind of the torque equals integral of that torque. And then that would represent that is the integral of these two. But it's not just a simple integral, because this term here, dA, is the dx times dy. So I have to perform a double integration there. And means that torque is going to be equal to the double integral of this kind of formula, this equation here, that is x tau yz minus y tau xz times dx times dy. But I know the values of those tau yz and tau xy, and then I can write it down. So that's going to be the double integral of something. So the first something is going to be x times tau yz, and tau yz, where is it? Here it is. tau yz, find it out, just got lost in the mess. I cannot see. Yeah, this one. Tau yz, or xz, the first yz. Anyway, I have to grab this one. Need to put it here. Yeah, and then this is going to minus y tau xz, and that one is this one here. We have done. Put it here, move it down here, and I'm going to remove or delete this one. Actually, to be one here, but this is going to multiply this dx dy. If I continue with this line, so I can take out those constant terms here, g theta, and then double integral of this, what's happening here. So I could just try to take everything off the parentheses and all of that. So this is going to be, the first part would be x squared plus x that multiplies the partial differential, the derivative of psi with respect to y. Yeah. Then the other one is going to be minus plus y squared. Yeah. Minus y that multiplies the partial derivative of psi with respect to x, dx dy. And then if I continue doing this, I can just rearrange it one more time. So it's going to be a double integral of x squared plus y squared plus x partial derivative of psi with respect to y minus y partial derivative of psi minus divided by partial derivative of x. Then dx dy. And this here is, I'm going to write it, kind of bring it like this. This is what is called the torsion equation for, for an element. I'm going to write it down here. And look how interesting this is going to look. So I'm going to have this one, and then write down here that this is torque equal to this. And let's make some kind of similitudes with what I had written in the beginning, that in here, what is it? This one. Sorry. This one. That torsion equation. So we have just found the torsion equation using same Venant. And then if I grab this one here and bring it down, oh, it's a mess. I'm just going to write it down as, sometimes it's phase. So TJG zeta. T divided by J, something is missing, equals to G theta. So this here is missing G theta. This here is missing G theta. So if I have T, I have G and theta. So this other term here is going to be J. So J, actually, I'm going to need to write it again. J is going to be equal to this secondary integral here. And let's give it a name to this. Y minus Y dx. Dx dy. So it happens that J is called torsional, sorry, it's not with C, torsional constant. And even more, this term G, actually, let me just look it up because I don't want to say something that is not aligned with the, just a second, torsional rigidity. Yeah, this product of J being the shear modulus times J, G times J is called torsional rigidity. Now, let's see an example of a circular section. So same methods apply also to circular sections, but also applies to non-symmetrical sections, which is a powerful feature of it. So what happens if we are in the presence of a circular section? So let me write it down here. So one of the benefits of having a circular section is that it is demonstrated that there is not going to be any warping, meaning that the warping component of Saint Venant can be disregarded completely. That is, if I mentioned here, well, coulombs is the one used for these, circular sections, and then there's no warping, and then we can use it like that. Then if I come back here, I can say that okay, if there is no warping, uh, so let's put it in this way. If I have the name of that equation is called the, sorry that I'm just scrolling too fast, but I'm trying to find the point of that. If I have the governing equation for torsion, this one here, and I say, okay, so this Laplace form of this equation equals 0. So for this to be somehow equal to 0, then it means that the derivative or term that is going to be differentiated has to be constant, meaning that this psi function or this psi is constant. Actually, there is something here that I need to recap. So this is 0, but you're going to find in text that this is going to be equated to a constant somehow, and that's something that you need to take into account. That is not that in this case for the formulation we're doing is 0, but this is something that has to be constant. Then just let me put a note here. Then if this is constant, it means that any partial, right, just jumping, any partial differentiation of psi with respect to y is going to be equal to this one here, with respect to x, is going to be 0. Then if I apply same Venant's formula, I'm going to have that, where is it? This one here. Just let me bring it actually. I hope it copies correctly. Yeah. And let me delete the stroke eraser. This one. Yeah. Then I'm going to know that these are going to be 0 and 0. And Saint Venant's formula is going to be simplified to the following. It's going to be minus y dy ds minus x dx dy equal to 0. Now I can put these signs to the other side, and this can be written kind of more a little bit better, like dy dy ds plus x dx dy ds dx ds. Yeah. If I integrate them, we're going to find out that I can integrate, for example, this part first and see what results in. That is, the first time I can say, or it's going to end up just being a single variable, something like ds times the integral of this y dy is going to be y squared divided by 2 plus derivative of ds of this part here, and this part here is going to be x squared divided by 2. And this sum is going to be equal to 0. I can collect terms also, meaning that derivative with respect to ds of this is going to be y squared plus x squared divided by 2. And this is equal to 0. So for this derivative to be equal to 0, it means that this term here has to be constant. Let me write it out here. So it means that y squared plus x squared. Actually, I can, this is equal, is constant. But if it's constant, I can get rid of the 2 and say that y squared plus x squared equals is constant. Great. Now, what happens if I see, we were talking about circular sections. So let me draw a circular section here. Like this. And a couple of lines. So let me align this with the center. Yeah. So I have a circular section there. And what is a constant actually that's going to happen there? Well, for this case, for a circular section, the constant is going to be kind of, if this is referred to the boundary of the surface, then for a circular section, this constant is going to be no other than the radius of that circular section. And actually, yeah. And if I go further and say, okay, but how to apply the, if I want to apply the torsion or that torsion equation that I found out before, which boils down to find out the torsional constant J for this circular section, how can I do it then? What would be the typical procedure to find out this J, which because G is known because that depends on the material, then theta is also that you can get to know, and because that's a type of deformation that you're going to have, but J, which is something that depends on the geometry of the section, how to calculate that? Well, let's do this simple example for the circular section. So if I have this circular section here, I could take a differential ring on that section, meaning it's something like this. So I can say something like, okay, I'm going to take one differential ring, something like this. Let me draw another one, maybe like this, yeah. So this is a differential ring of element there. Now this is going to have a differential area. The distance from the center to the beginning of that differential element, that's going to be r. The distance from the center to the outer circle, I'm going to call it uppercase R. And what else? And this kind of, this one. The thickness of this ring, I'm going to call it differential of radius. Let's find out the torsional constant, this one here, to move it a little bit up. So in this case, I know that these terms are not existing here. Then I can rewrite this as follows, kind of in a simplified way. J, torsional constant, is the double integral of this x2, well, x squared plus y squared times dx dy. But the x dy somehow represent the area of the element, and the sum of this one here, we have said that that's equal to the radius square of the circular section. So I can write down this as double integral of radius square times dx dy, and I can reduce that even more by saying that j equals to just the integral radius square of this differential area. Now we need to find out if the differential of area or r is in the differential of area, or one is part of the other. So as a circular segment here, the differential of area is going to be equal to what? I'm going to write it down here. Is equal to the inner radius, kind of the whole circumference here. That's going to be 2 times pi, the radius, that's the circumference. So that's the internal surface times, or it's kind of line perimeter, times the dr. That's going to give me the differential of area there. Then I can substitute that in here and say that j equals to integral of r squared times 2 pi r dr. Then if I operate this, kind of, again, doing more steps, 2 pi integral of r squared, r cubed, sorry, dr. And if I perform the final integration of this segment here, that's going to be ending up at that j is 2 pi r4, r to the power of 4, divided by 4, which, again, keep simplifying. It's going to be pi r4 divided by 2. If you have seen this equation before, that's equivalent to the polar moment of inertia of a cylinder, which is perfectly coincides with that, the Coulomb's theory says. So this is the polar moment inertia of a cylinder. Okay, but this is still not finished. So let's bring the torsion equation, not torsion equation, but yeah, torsion relation. We knew that this one here, this one, the torsion equation, Tj theta. T divided by J equals to G theta. Then I'm interested to know this twist angle. You're going to see why. T, G, J. So this is the torsional, what was I call it? Torsional rigidity. Yeah. Then, if we want to know the stresses, kind of, or how stresses are being produced inside of that section, then let's bring same Venant. And say, okay, I know that there are going to be a couple of stresses. The first one is tau z, and the second one is going to be tau yz. Know that both start with g theta, and I know that both has certain terms here. And those terms are going to be, just get it lost all the time, here they are. So y theta is with x, xz is with minus x minus y. Okay. So x is with minus y plus the partial derivative of this function with respect to x. And in this case, it's going to be with the x minus plus partial derivative of psi with respect to y. And as I know that this psi function is 0, then I'm going to end up with these two simplified shear stresses. That are going to be minus g theta y, and the other one is going to be tau yz is going to be g theta x. Now, one reason I grabbed theta out of that torsion equation is to be able to use it in here. If I substitute both of those there, then I'm going to have that tau xz equals to minus g t divided by gj, the torsional rigidity, times this y. If I keep simplifying this, well, no, this goes out with this one, and then I'm going to end up having that is equals to minus t y j. And in this case, tau yz, the same, of course, and t divided by gj, then this x in here, and then this is going to be equal to t x j. So I have two shear stresses. If I wanted to know what's the, let's say, resultant stress of that, well, I have to use the Pythagoras theorem in this case, and I can say that, okay, the resultant stress you're having this circular section is going to be equal to the square root of adding the squares of those two shear stresses there. Then that's going to be that shear stress of what? The first one. Let's grab the first one that we have there. Tx divided by j square plus the other one would be minus ty divided by j. And if I keep working, just to be a little bit more specific, that's going to be t square, x square, j square, plus negative sign goes away, j square, sorry, y square divided by j square. And I can bring out certain terms like, for example, t and y and j, sorry. There's going to be square of this one here. And we know what this thing here is, what is inside of this term. This equals to r. Then I can write that the shear stress, the maximum shear stress actually in this element is going to be equal to the torque applied divided by the torsional constant multiplied by the radius. And that's the formula that we have been using in most of our cases. Let me bring it. So we used same Venant to determine the maximum stresses found on a shaft or of circular section with a torque applied. And it was very, let's say, consistent with the information we have given, meaning that if we wanted to find out the maximum stresses, because at the end, we always want to find out stresses so we can compare that to any reference values, such as the yield stress or something else, and to find out what are the maximum stresses on an element subjected to torsion, then if the section is circular, well, it's piece of cake because you don't have to take warping into account. But if you have a non-symmetrical section, it means that you have to work a little bit harder to get what are those equations that define the boundary of the surface so you can calculate the torsional constant and then find out what are those stresses you're looking for. And one thing that plays an extremely important role are the shear center of the piece that is not going to be coincident with the central axis of that. Something that we will see in an exercise. But I want to close what I was going to give you today at this point with saying that this is a simplified way of seeing Saint Venant. It could be done very much, much complex way. But so far, with what we have to do in the course, this works for us.